Session of the Fellows meeting. But before I start, I should say that we found some euro notes here. I will not tell you how many euros they are. If you do not claim them, it goes to the ITAMP General Fund.
So I lost actually 1,000 euros.
700. So you have until the end of this session.
I see what you did there.
We should begin. The first presentation is given by Bihui Zhu. So when, before the pandemic started in January of, I think, I remember correctly, or sometime in February, Bihui received an offer for a faculty position. She was in her last year at ITAMP. And in the beginning of March, all of the calls for shutdowns went out. And within a matter of, I think, 2 days, 3 days, she received an email that the offer was rescinded. Of course, at the end, things worked out. She is at the University of Oklahoma, but those were really trying times in all respects. So, without further ado, first let me get the light. I need my glasses. Yeah. Oh, thank you. Good test. So, without further ado, Bihui, yes, please go ahead.
Okay, good afternoon, everybody. I would like to start by thanking Hussein for organizing this wonderful workshop. It is a great pleasure to be back again at ITAMP, especially after COVID. And also I would like to thank Hussein for his support during my years at ITAMP. So since this is the last session of this symposium, you have already heard many nice talks about the interesting dynamical behaviors of quantum systems driven out of equilibrium. So for example, you have seen this first figure from Misha's talk yesterday, which shows a pioneering experiment done in Misha's group using readable atom arrays, which demonstrates a peculiar type of non-thermal behavior the quantum many discussed. You have also seen this second figure, and from Anna Maria Ray's talk yesterday, which shows that polar molecules become quantum correlated once they are pinned inside deep optical lattices. And in this third figure, it shows the experiment done with trapped ions, where both spin squeezing and anti-spin squeezing were observed. And this is also a work done by Anna Maria together with John Bollinger's group. And in this last figure, this shows another experiment done with a quantum gas microscope at Marcus Greiner's group at Harvard, where quantum thermalization was studied through the lens of the entanglement of growth. So in this talk, what I would like to do is to show you 3 additional setups where we can find interesting quantum many-body dynamics. So in particular, you have seen many nice talks where the systems consist of particles with 2 levels or qubits. And I would like to show you a system where the particles have a larger local Hilbert space. And this is a collaboration with Anna Maria and the experimental team of Bruno Lambert-Torre at Paris, where the ultra-cold chromium atoms are trapped in deep 3-dimensional lattices. And then, departing from such quantum systems where the most relevant processes are coherent, I will discuss about the quantum many-body dynamics in the system where there is a strong dissipation. And as demonstrated in the recent experiments done in Andrei's group at Caltech. And then along the goal of addressing open quantum systems, I will discuss how we can use measurements to generate a significant quantum entanglement and non-trivial dynamical phase transition. So for those who are not particularly familiar with chromium atoms, let me first give a very brief introduction. So roughly speaking, as we know that the magnetic dipole moment of an atom is proportional to its total angular momentum. And the resulting magnetic dipole-dipole interaction is quadratically enhanced by this angular momentum. So for bosonic chromium atoms in their ground state, they have a 0 nuclear spin and a total electronic spin of S equals 3. And this gives rise to much stronger interactions compared to systems where there's a tiny spin. With the presence of a large external magnetic field, the dipolar interaction takes the form of an XZ-type Hamiltonian, but with a spin operator that is higher than 1/2. So in the Paris experiments, what they have been able to do is to cool down these chromium atoms into quantum degeneracy and then load them into this deep three-dimensional orbital lattice with high filling fractions, such that the motional degrees of freedom becomes irrelevant, and there is also significant spin-spin interactions, which becomes the most relevant energy scales compared to other processes such as decoherence. So this system provides a nice platform for simulating this long-range XZ model. Then to probe the resulting quantum manipulated dynamics, a natural way is that we can just prepare the experimental system in some initial product state where there are no correlations between atoms. And then we just let the system evolve under this XZ Hamiltonian. And then as we would expect that, and this coherent dipole interaction will generate correlations between atoms. And so then we measure some observables to probe this correlated quantum many-body state. It is worth mentioning that in the experimental system that we considered, in both the initial state preparation and the final readout, they are global operations. So they don't control or probe some atoms locally. So you have also heard from several previous talks that, so for such an interaction quantum many-body system, generally the system will reach some equilibrium eventually. So from the perspective of closed system quantum simulation, so if you look at a small subsystem, and then the rest part of the system sort of serve as a bus. As such, the local observables measured at a long time can be simply obtained from a thermal ensemble. Now the question is, and can we observe such a simulation in the experimental system with the chromium atoms? So in order to probe quantum simulation in a many-body system, one way is to consider a setup as shown in this figure, which is taken from a frequently cited review paper on quantum simulation and many-body localization. In such a setup, and the system is initially prepared with some non-uniform atom configuration across lattice size. And then by checking the atom configuration over time, and then one can see how the system relaxes. However, as you can see, this would require the capability to measure the local size. But as mentioned, this is not yet available in the experimental system that we considered. However, it turns out that actually for these chromium atoms with multiple internal spin states, and there is actually another way that we can do this. In fact, as mentioned, the chromium atoms, they have a large spin, and with S equals 3 and the 7 internal spin states. And one can sort of view this spin states as expanding a synthetic lattice dimension, so that the atoms actually can hop along this synthetic lattice and under the effect of this coherent dipole exchange. So therefore, this leads to a change of population over this synthetic lattice size. And in thermal equilibrium, and one would expect that there would be some certain distribution of populations along this synthetic lattice. Therefore, this means that instead of resolving the real lattice size, we just need to resolve the population of this spin state. And this is something one can do just by using the Stern-Gallacher separation. So therefore, the experimental sequence is just that we can use some global and pulse to excite the system, and then we wait some time, and then we perform a collective measurement to find out the number of atoms populating different spin states. So this is what the spin dynamics looks like. Here, different colors correspond to the fractional population on different spin states. And for the initial state considered here, which is a coherent spin state with a pi-half rotation, and there is a symmetry in the plus minus spin states. And we also perform the numerical simulation for this long-range XZ model, and this is represented by the solid lines here. In fact, and for such a many-body system with thousands of atoms, it's very challenging to evolve the quantum many-body wave function. So what we did was that we used an efficient numerical method, which we call this GDTWA. I'm not going to delve into its details here, but I would be happy to explain more after the session in case anyone is interested. But as you can see from this comparison between the solid lines and this experimental data, there is a good agreement. In addition, we also calculate the classical dynamics, which are represented by the dashed lines, and they clearly deviate from the experimental data. So this indicates there is the presence of quantum correlations in the experimental system. And so also, for the longest time scale available in the experimental data, and the system more or less reaches equilibrium, and more or less reaches steady state. So if we plot this final distribution over spin states and compare it against the thermal prediction, and then we indeed find a good agreement. So I mentioned that atoms become correlated and due to this coherent dipole-dipole interactions. The natural question is that how can we measure this spin-spin correlations in experiments with only collective measurements? And so it turns out, again, the large spin nature of the system provides a solution. So the idea is actually quite simple. So from this fractional and population on spin states, we can just obtain this collective magnetization as well as their variance. And for this XZ type of Hamiltonian in the system, and this variance is actually a conserved quantity. But we can also view this variation and from these two contributions. The first contribution comes from the spin fluctuation from each individual size, and so we call this inter-side correlations. And in fact, this is trivial for a spin 1/2 system because the SZ square is simply 1/4 for this system, but it becomes non-trivial for higher spin systems. And also, it is related to the fractional population that I mentioned. So therefore, and this part of inter-side correlations can be obtained and from the collective measurement in experiment. And then the other contribution is this connected two-body spin correlator. And this actually represents the part of a correlation that's generated by many-body effects. And this is the part of correlation that we are most interested in. So although we don't have the capability to directly measure these individual spin operators for different sizes, but because now we can measure this variance of the total spin projection and also this intra-side correlations, and this also allows us to find out this spin-spin correlations from experiment using only collective measurement. And theoretically, we can determine the initial growth of spin correlations from a few parameters of the experiments. And at the long time, the system thermalizes, and so therefore, we can also obtain an expected value for the generated spin correlations. And what the experiment finds indeed agrees with our theoretical prediction. And so here, and this long dashed line shows this thermal equilibrium values, and this dotted line and shows this initial correlation growth. And this solid line is again this numerical simulation. So now we have a way to quantitatively characterize the spin correlations in such a many-body system. And you may notice that there appears to be some deviations. And this is in fact related to the fact that the experimental system is not completely closed. So there are some atom losses. Then it made natural for you to ask that how about the quantum many-body dynamics if there is a significant coupling between the system and the environment. in fact, for this audience, and so perhaps a familiar example is the photon emission from two-level atoms. For a collection of coupled atoms, the atoms can emit photons and cooperatively, such that they generate photon emission that is much stronger and faster than independent atoms. And this is a decay superradiance. If you look at the quantum many-body states represented in the angular momentum basis, and what you can find is that there are states and with increased decay rates, and there are also states with this suppressed decay rates, and this corresponds to superradiance and the subradiance, respectively. And this is demonstrated in the recent experiments done by Andre's group at Caltech. So in their system, many spins are coupled to a lossy cavity. And so after adiabatically emulating this photon degrees of freedom, their system can be described by a master equation with collective decay of the collective spin excitations. And in addition to non-collective processes that comes from single particle defacing and spontaneous emission. And there is also a coherent driving pulse that is applied initially to prepare different many-body states. And the photon emission measured in the experiments can also be theoretically calculated by just looking at these collective spin operators. So now if you look at the quantum many-body state again, what happens is that these non-collective processes actually would couple this superradiant decay ladder into this subradiant states, where there are many more subradiant states. So if we increase the driving strength, and this will actually allow more passes for such couplings, and therefore, this will enable a significant population of these less radiant states. And this can be confirmed by a theoretical calculation by solving the master equation. So as you can see, when the power strength, driving power strength is increased, and so there is indeed increased population in this subradiant subspace. And here, for simplicity, this subradiant subspace simply means the part that is outside this collective decay manifold. And correspondingly, if you look at this peak photon emission as depicted by this red line here, then you also see that it starts to drop, and when there is significant population on this subradiant subspace. And these features are indeed observed in the experiment. So as you can see here, at the fixed driving strength, and the photon emission is much faster than independent emitters. And after some time, when those superradiant states have already decayed, and then a slow tail shows up and demonstrates the contribution from those subradiant states. And the peak photon emission also varies with this driving strength as we expected. But you also see that there is an increase again with sufficiently strong driving power. This is because the experimental system actually contains emitters at different local detunings. As a result, more of them get excited if there is sufficiently strong driving power. So in the rest of the time, I would like to turn to a different setup, which is motivated by the recent development of these digital quantum computers. And so as you have heard about from Misha's talk yesterday. And so in this case, we actually consider dynamics in a quantum circuit. So in typical quantum circuits, and there's a coherent unitary gates applied repeatedly to entangle qubits and scramble quantum information. And when the measurement is made, and what happens is that, so it will collapse the quantum state and disentangle the qubits and from the rest of the system. So although this setup looks different, but actually it's closely related to the open quantum many-body dynamics. And so this randomly implemented measurement corresponds to a quantum jump. And the time evolution under a sequence of such unitary gates and measurements corresponds to a quantum trajectory. So at the trajectory level, the state of the full system remains pure. And checking such a quantum trajectory corresponds to monitoring the measurement outcome and perform post-selection. So as such, in this system, the unitary operations and the measurement provide two competing processes. One is for generating entanglement, the other is for destroying entanglement. As a result, depending on how frequent these measurements are made, and there is a dynamical phase transition. So with the rare measurements, and then one would expect that and a local subsystem will quickly get entangled with the rest of the system. But if the measurements are very frequent, and then this will suppress the growth of entanglement. And so there are two distinctly different dynamical behaviors that shows up and also separated by some critical measurement rate, PC. So below this measurement rate, the entanglement generated at a steady state actually will increase with system size corresponding to a volume law phase. But higher than this measurement rate, this is independent of a system size. This corresponds to an area law phase. And this is a so-called measurement-induced phase transition. And this has been actually demonstrated in several quantum processors. And in such cases, and so it's clear that the role of measurement is destructive. However, measurement can actually also be used in a beneficial way. And this possibility becomes to be drawing more attention in recent years and in the context of quantum manipulated dynamics. But typically, multi-qubit measurements will be needed to generate volume law entanglement. Here instead, and we consider a quantum circuit consisting of only measurements. And we implemented two types of measurement, this XX measurement and the ZZ measurement. And these correspond to these boxes here, represented by different colors. These measurements are made on pairs of qubits. And so these qubits do not have to be nearest neighbors, but the rate of measuring them would decay with, in a power law form with their relative distance. And so to give you a more concrete idea of these measurements, so we can consider an example where we perform a ZZ measurement with a measurement outcome of +1. And what this does is that it will collapse the quantum state and in such a manner that the measured two qubits measured and will just end up with some particular parity states. So in our circuit, there are no unitary operations at all. And these measurement operators, they are Clifford operations, and so this allows us to efficiently simulate dynamics using the stabilizer formalism. So we calculate the half-chain entanglement entropy for the circuit dynamics starting from initial pure state. And then what we find is that there are also qualitatively different behaviors in this entanglement dynamics for different range of measurement. And if you look at the steady state entanglement generated, and then the scaling behaviors also differ from each other. There are different regimes, again, depending on the range of measurement. Here, alpha and a larger alpha actually correspond to a shorter range of measurement. So what we see is that if the measurement is short-ranged, and then the entanglement generated is actually scales as an area law form. But with a long-range measurement, and then there is a volume law phase. There is also a region with intermediate range of measurements where the entanglement increases with the system size in an algebraic way, but it is slower than the linear scaling. It is also worth mentioning again that, and so this entanglements are actually generated by measurements instead of by scrambling unitaries. And we also examine the purification of quantum states in such a circuit. This corresponds to the dynamics of the total entropy of the system starting from initial mixed state at infinite temperature. And then again, what we see is that there are qualitatively different behaviors where the system can quickly get purified, or it can actually keep the encoded quantum information for a very long time. And it is also worth mentioning that in the previous studies of circuits with unitary gates and also single-site measurements. And what they find was that the purification transition actually aligns with the entanglement phase transition starting from a pure initial state. And this is not the case here. And because in our setup, measurements play very different roles. So this brings me to the end of my talk. So in summary, I have demonstrated how we can probe quantum symbolization and measure the build-up of spin correlations and in the real experimental system through just a collective measurement. I have also discussed the superradiant and the subradiant dynamics in a quantum system with strong dissipation. And in the last part, I showed you that by using long-range correlated measurements, one can generate a significant entanglement. And finally, I would like to take this opportunity to thank my collaborators with special thanks should go to Anna Maria. And thank you all for your attention. I'd be happy to take any questions that you may have.
Thank you. So, questions? Quick.
So I think with the superradiant decay, I missed a little bit this. What was the power, or when you say driving power?
Yeah, that's just they will have this pump into the cavity that will correspond to here. So and what we did is that actually this will be in the photon degrees of freedom, right? But because they have a really lossy cavity, and then we can derive an effective model which is represented here. And then this driving term, and which is originally in the photon, and it will goes into such a kind of a Hamiltonian term. And so we have this parameter here, and then it actually drives the spin. But they actually
so in this dynamics, you always have the driving on. It's not that you excite the atom, but you have an always on driving? Is that?
Yeah, so no, actually, as I sort of mentioned, and so what happens is that in this coherent driving is applied initially to prepare the different manipulated state. And then it's sort of, you can imagine it's sort of the sequence, they apply some driving. And so, but this driving pulse is more or less long enough that, and so you can imagine that you have like the system will evolve under this full master equation, and with this additional driving term, and then sort of reach a steady state, and then this driving pulse is turned off, such that, and then what will happen is just afterwards there will be this dissipation.
Okay, so they have more time to move to the, or more spins can scatter to the subradiant states.
That's right.
During this initial point, okay.
That's right. Yes.
Okay, thank you.
This 984 nanometer laser is into the open side of the cavity.
That's right.
Thank you. Very nice talk, Bihui. I have also a question about that. So, the prior Hamiltonian, when this Hamiltonian has a second order phase transition or one first order phase transition.
But yeah, thanks for pointing that out. Here we are actually in this dissipation dominated regime.
Exactly, in the dissipation dominated regime. So okay, so you can never make the drive stronger than n times gamma.
Yeah, I think this is sort of related to the first question, and that's actually here what we did is that we really just probe this photon emission, and so the driving is actually turned off. It's kind of like we don't directly probe this kind of structure of this Hamiltonian, and we don't kind of see the phase transition here, but instead, because what they do is that just read out this photon output, and so that allows them to monitor and this kind of emission dynamics of these photons after turning off the driving power.
Yes, but during the drive process, you don't see any difference because I mean all the time you drive when you do the preparation, you go to where where is the initial state pointing, like at the equator, or you are.
So that's a kind of exactly a kind of sort of the difference here, because they don't really kind of resolve that state. Yeah. So it's kind of like they start from some kind of ground state, right? And that means there is no excitation, and then apply this driving and just wait for sufficient time, right? But then they do not kind of directly measure these spin states, right? And so what they do is that they just read out these photons emissions.
Yes, but in principle, well, we can talk. But I mean, depending of how strong you drive,
that's right.
The steady state when you do the driving, can have different features.
That's right, but that's sort of like what is mentioned here. And also maybe a difference that maybe I should also point out is that, and so there is actually significant non-collective process here. Oh. And so which is why it's kind of like some of this kind of collective kind of phases that you can see in this collective model may not really apply here.
Okay.
And so something that I did not mention is that, and so there is actually a significant inhomogeneity in the sense of this detuning term here. So that's actually also kind of plays a strong effect of driving kind of this state from this collective superradiant ladder into the subradiant space.
Okay.
Yeah.
Okay.
Thank you. Thanks a lot for the nice talk, Bihui. Can you just go to your slide with the entanglement, entropy with the area and volume laws? Just I think you went a bit too fast. So the colors on the left correlate to the colors on the right-hand side here, or no?
That's actually a great question. There is some sort of technical details here. So actually here, as you can see, and so in this sketch with a kind of a entanglement scaling and phase diagram, and so it's kind of like this particular line, which corresponds to this measurement rate, is kind of a slight, it's sort of special in the sense that it is actually kind of the scaling is different. The entanglement scaling is actually logarithm of L along this line. But nevertheless, and so what we can see is that, and so here, it's kind of, in terms of entanglement scaling, in short answer is that in terms of entanglement scaling, and so this actually doesn't correspond to, and so this part, exactly, it actually corresponds to this line.
So, for example, the red curve is not volume area law, or is it? This is where...
So for this line, it is, but the complexity comes from this part. Right, so it will sort of correspond to like a here.
I see.
Yeah.
And this peak behavior, this peaking behavior, how do you interpret that? How do you understand that?
Yeah, this is actually a nice observation, and this is actually a transient dynamics, and so generally it happens when there is a sort of sufficient long range and measurement, and then what happens in this case is that you can imagine that, and so because we make this long range measurement, so even for some distant qubits, and then once this measurement is made, and then immediately they sort of get entangled with each other. However, this generally doesn't really correspond to the true steady state of the system, right? So in the end, and so when there are sufficient amount of measurement so that this local qubits, it can actually have the chance of getting entangled with more over there is surrounding qubits, and then it actually will reach a state that may actually have a different entanglement structure. And so we have a way and to sort of probe into this entanglement structure, but that will go into more technical details, but I will be happy to talk about more after the session.
Okay, thanks a lot, thank you.
If not, then join me in thanking Bihui for a nice talk.